This is the fume hood team for EGR 190. To begin, a fume hood is a ventilated enclosure where chemical reactions are carried out. Our client, Duke University Facilities, operates approximately 250 variable air volume fume hoods, and when the sashes are left open, enormous amounts of energy is wasted. Existing solutions to the open sash problem are inadequate. Those based on behavioral modification, such as signage and general awareness, are inconsistent, and existing hardware retrofits are prohibitively expensive and hard to install.
Our solution was to build a device which can detect when a fume hood is not being used and automatically close the sash. In addition to this basic function, we wanted our device to be out of the user's way, not compromise the user experience of the fume hood, not be permanently attached, accurately detect users, and be safe to use.
Last semester, we designed and tested a device to solve this problem. However, this solution was limited by its reliability, attachment to the fume hood, and fidelity of the electronics. This semester, we decided to answer these problems with a complete redesign of the closing mechanism, upgrades to the electronics, and a new control program. Additionally, we designed everything for a new fume hood model which demanded new forms of attachment.
Our final prototype involves three main components: a mechanism to close the sash, manual controls, and a system to detect user activity.
The closing mechanism was inspired by the vertical axis of a 3D printer bed and consists of two rods in parallel along the vertical edge of the sash. One of these rods is threaded, is 26 inches long, and attaches to a 12-volt DC motor via 3D printed connector. The other rod is unthreaded, 28 inches long, and extends up past the threaded rod into the motor's casing. Both rods rotate freely in the bottom rod holder. Placed on the threaded and plain rods is the pusher. The 3D printed pusher is a 2.5 inch by 2.5 inch block with a nut and hole that correspond to the rods. The edge of the pusher is able to push down on the bottom edge of the sash to execute the sash's closing. As the motor turns the threaded rod, the pusher is able to move up and down, using the plain rod to maintain contact with the bottom edge of the sash. The pusher also has a 2-inch square rod that extends from the left edge of the pusher towards the fume hood's wall. This rod presses a limit switch once it has been raised to the open sash position. Once the pusher has pushed the sash to being completely closed, the top of the sash presses a separate limit switch.
The motor's 3D printed casing has two pins that fit into two holes on the main attachment piece. The main attachment piece fits into a 1 inch by 1.25 inch notch at the top of the fume hood and extends down to the top edge of the sash. This main attachment fits snugly in this notch, but also has a clip that holds onto the edge for extra stability.
Our device has two manual controls for lowering the sash and overriding the closing mechanism. As a convenience, the user can press the manual lower button to engage the sash closing mechanism. The manual override button is a safety feature which can either disable the closing mechanism altogether while the sash is still open, or prevent the sash from closing any further when the closing mechanism is engaged.
The user detection system, which has not been modified since the previous prototype, involves a Raspberry Pi with a camera mounted to the bottom corner of the opening. During installation, the installer tells the camera which region of the screen represents the inside of the fume hood. During normal operation, the Raspberry Pi scans frames for significant changes in pixels within the specified region, which indicate user activity. Whenever activity is not detected for 5 minutes, the sash is closed. After testing other possible methods, camera motion detection was the most reliable, unobtrusive, and easy to install means of detecting users.
The device is controlled by a Python program running on the Raspberry Pi. The program uses a state machine model. At any given moment, the system is in a particular state defined by a specific combination of input and output values. The program monitors digital inputs and the camera server for changes in the state of the fume hood system, and the program transitions to a new state when particular changes happen. This approach was chosen for being robust, scalable, and easy to model.
All components were attached to the fume hood using command strips for easy installation and removal.
We evaluated the extent to which our device met the design criteria by measuring its compactness and ease of installation, testing the consistency of the control program, and fielding user feedback.
We wanted our device to be compact so that it would not limit accessibility to the inside of the fume hood. Originally, we discerned that the device should not extend out more than 2 inches from the face of the fume hood for all regions of the hood. Additionally, the device should not extend more than 4 inches out from the frame of the hood. This was tested by measuring local maxima with a ruler. Our device was able to get within the 4-inch limit, but was only able to get down to 2.5 inches from the face of the hood. Though the compactness criteria were not completely met, we believe the spirit was fulfilled.
Ease of installation was a major design criteria first outlined by our original client. The device should take less than 30 minutes for 3 people to install. The first time we tested this, it took more than 45 minutes for 3 people to install. However, every test since took less than 20 minutes. This criteria was not just met by increased familiarity with the installation process, but also with changes in attachment methods. Though we did not test ease of installation for one person, we suspect that it should take less than 90 minutes for one person to install.
We were concerned with the consistency of user detection and the state machine program. The user detection system should ideally produce no false positives to maximize the amount of energy saved, and more importantly, no false negatives to ensure the device does not close the sash on unsuspecting users. We repeatedly tested whether the user detection system registered activity when there were either activity or no activity. We found no false negatives, but there were many false positives caused by shadows or reflections in the glass of the sash. Although the ideal criteria was not met, false positives are not as problematic as false negatives.
We requested several undergraduate and graduate students with lab experience to test our device. We collected their feedback in a brief survey asking how the device impacted their experience of using the fume hood, whether the device interfered with their work, and general critique of the device. They found that the device was sufficiently compact and that it did not significantly interfere with their work. They were critical of the amount of noise created by the motor, measured to be approximately 66 decibels, and the overall usefulness of the device. The device satisfied the criteria of being out of the user's way, but failed the criteria of not significantly worsening the user experience.
Our device partially or completely met all the design criteria. The prototype demonstrates that our ideas work, but it has not matured enough to install on actual client fume hoods due to limitations on testing accessibility and attachment. However, it is an improvement on last semester's work, and the concepts behind the most recent device show promise for future development. Moving forward, we would like to reduce the motor's noise, increase the lowering speed, investigate multiplexing Raspberry Pi cameras, add obstruction sensing, expand from vertical to horizontal sashes, and enhance compatibility with different fume hood models.